This video is the continuation of the proposition continuity of measure. Okay, so here in the previous video I have explained you case 1 of this part of the statement. Okay, I told you that this part of the statement having two cases. In case 1, what you will do is you will take a measurable set from this sequence and you will say this measurable set is infinitive. That is what our case 1. In case 2, you will take another one measurable set from that sequence, that is AK, and you will say measure of this measurable set AK is less than infinitive. What is the meaning of less than infinitive? Less than infinitive means you are saying measure of this measurable set AK is finite. In case 1 is you said measure of this measurable set is infinite, and in case 2 you are saying measure of this measurable set is finite. Okay, so to prove this case 2, what we are going to prove this. Okay, in case 1 also you will prove this. In case 1 you proved it. You can find that video on my measure and integration playlist. Okay, go and check out it. And in case 2 also you are going to prove the same. Okay, in both cases you will prove this. Okay, so in case 2, to prove that, what you have to do is you have to define two things. First one is A naught equal to empty. Okay, the set A naught equal to empty. And also define what you will define, CK is equal to AK difference AK minus 1. You have to put this. Okay, this is also correct, AK minus 1. This is also correct. You can put minus or you can put this. Okay, in textbook they have used this simple, so we can also follow that. So also define CK is equal to AK difference AK minus 1. Okay, there is a name for this symbol, that is tilde. I hope you know that. Okay, so you are defining these two, and now from this line you can say this. Then sequence CK, K equal to 1 to infinitive is disjoined. From this line you are saying this. How you can say that? Here CK is equal to this, right? When you put in the place of K, when you put 1, you will get C1 equal to A1 minus A0. When you put 2, you will get C2 is equal to A2 minus A1. Similarly, you can put for till infinitive, right? So here, what you will come to know is, look at this C1. When you find C1, what you are doing? You are subtracting A0 from A1. When you find C2, in C2 what you are doing? You are subtracting A1 from A2. So you will do for all C1, C2, C3 till infinitive. So what you will get is, you are not going to get any common elements in C1, C2, C3, C4, C5, etc. till C infinitive. Is that clear? So if there is no common elements, then what will happen? They will be disjoined, right? Only if there is a common element, the figure will be connected. Right? If there is no common elements, then the sets will be disconnect, or you can say they will be disjoint. So that is what is happening here also. So here from this you can say CKK is equal to 1 to infinitive is disjoined, and you are writing this also. So you are writing this. What you are understanding from this? You are having measurable sets A1, A2, A3 till infinitive, right? You are finding the union of that. A1, A2, etc. till infinitive. And also you are finding the union of this C1. You are finding C1, C2, C3 values also, right? From this. So when you find the union of that C1, C2, C3 till C infinitive, you will get a value. And from here also you will get a value. That both value will be same. Okay, so that is what you are writing here. Now you are taking measure on both sides. So you will get this. Now this can be written like this. You have a proposition. The name of the proposition is countable subadditivity of mu. You are using that proposition here. By using that proposition, you can write like this. This can be written like this. That is, instead of union k equal to 1 to infinitive, you can put summation k equal to 1 to infinitive and bring this bring this mu like this, mu of ck. Okay, you are bringing this union outside. When it comes to this place, then it becomes summation. Okay, this is happening how? You are using proposition. What proposition? Countable subadditivity of mu. Okay, hope you got my point. Now you are writing this summation k is equal to 1 to infinitive mu, and in the place of ck you are going to substitute this value. Okay, that is what happening. And now what you are doing is, here you are making an adjustment. That is, instead of here summation k is equal to 1 to infinitive, instead of putting infinitive, you are putting n. And the same thing you are writing, but here you are writing limit this n tends to infinitive. You are making an adjustment. This can be written like this. Okay, limit n tends to infinitive and summation k is equal to 1 to n. It means what? This n tends to infinitive. The same thing you are writing, but in a different manner. Okay, that is, you are making an adjustment. That is what in simply I can say that. Now now you are writing mu of ak minus ak minus. Okay, ak minus ak minus 1, or you can put this symbol, whatever, everything is right. Now write this limit n tends to infinitive and apply this value. So when you put k equal to 1, you will put mu of a, you will get mu of a1 minus mu of a0 plus summation, right? So plus. Now when you put a2, you will get mu of a2 minus mu of a1 plus etc. till nth term you are writing. When you write for nth term, mu of an minus mu of an minus 1, right? You will get this. So all the terms will get cancelled except this minus mu of a0 and mu of an. So you are writing that in the next step. Now from this, you are in the first line of case 2, you have defined a0 equal to empty, right? So that is what you are using here. Mu of a0 is equal to mu of, in the place of a0 you are putting empty because you have defined like that. So mu of empty, measure of empty is what? 0. So that is what you are writing here. So limit n tends to infinitive, this becomes 0, and you will get limit n tends to infinitive mu of an. Now here in our proof, the right hand side is like, in the right hand side you are using k, not n. Okay, so you are just changing instead of n you are putting k. Okay, the value is not going to change. Okay, instead of this n you are putting k. Okay, in both places. So you will get this. So write the left hand side. Okay, write the left hand side. What do you have in the left hand side? This, right? You're having this in your left hand hand, right? Left hand side of this equal to, so that you write this equal to, and you will write this. So you have proved. So in case 2 also you have proved what they have asked us to prove in the first part of this question, first part of this statement. Okay, now we are moving on to prove the second part of this statement. Okay, I will explain you the proof of this part in another video. Okay.